Okay, for example number 2, we're going to still talk about neutralization, and it's going to start with, to standardize a sodium hydroxide solution, a student plans to titrate a solution with monoprotic KHP. She dissolves 1.3009 grams of KHP in water, adds phenolphthalein, and titrates to the endpoint. Now, it took 41.20 milliliters of sodium hydroxide to titrate the KHP. Okay, what the heck does that mean? We want to know, what do we want to know? The concentration of sodium hydroxide. So let me sketch this out for you to kind of give you a general idea of what we're looking at. First off, we need a balanced chemical reaction. Now, they gave you the big giant formula for KHP, KHC8H4O4. We usually abbreviate that as KHP because this is the phthalate ion, and we just don't want to write it all out. Well, we react that with sodium hydroxide, and we get, and before we even go any further, I want to go ahead and get rid of the potassium and get rid of the sodium because they are the spectator ions. Okay, the flat out spectator ions. So just to show you what that would look like, we have a hydrogen ion, and this phthalate, however you want to write it, well, maybe to make things easier, I better leave it there for right now so as to not confuse you. Or at least hopefully not confuse you as much. So if we took off the potassium, we've got HC8H4O4. This whole thing would have a 1- charge because I ripped off the potassium, so there's my reaction. I'm reacting it with hydroxide. Now the chemistry that's going to take place, here is my acid and here is my base. So the hydrogen is going to be donated to hydroxide and make water, as well as leave us with that phthalate ion. So C8H4O4, which is now 2- because we took off the positively charged hydrogen. Now again, the chemistry that's taken place here, what we have is a burette that would have sodium hydroxide in it, and that sodium hydroxide, we're looking for the molarity. Okay, that's what we're looking for up here is the molarity. The volume is 41.20 milliliters. Okay, or remember what we're looking for, since its molarity is moles per liter, so the volume I already know is going to be 4.120 times 10 to the -2 liters. So I know the volume. So I got to figure out the moles, which if I had just told you in the very beginning that I started with 1.3009 grams of KHP and you wanted to know how many moles of sodium hydroxide, you would have been golden with that. Okay, and we have to again think about our net ionic, but when it comes to when we start to go with grams, we have to be careful with solutions in aqueous environments. We have to have a working knowledge of both our molecular as well as our net ionic, because when we deal with molar masses, we have to go back to what it would be originally. So regardless, I'm going to start, I still just have to go from grams of KHP to moles of sodium hydroxide, and then I can figure out my concentration. So from my molar mass, 1.3009 grams, I'm going to use KHP here because it's easier to write, and we'll use KHP. The reason it's a common acid that we use in reactions is because it's monoprotic. We like one-to-ones because they make the math much easier and much more straightforward. And we usually try to do one-to-ones in lab, not all the time, but a lot of times to make it easy, and that's why KHP is common. So we take the 1.3009 grams of KHP. Now to show you that, we would have had an Erlenmeyer flask, we would have put the 1.3009 KHP, we would have dissolved in water. And the reason we would have known the reaction was over is as soon as we went 41.20 milliliters, it would have turned pink. And it would have turned pink because all of the, as you're adding in the hydroxide in the beginning, adding in the hydroxide, it turns it clear. It reacts with the acid, reacts with the acid, reacts with the acid. Well, as soon as you use up all of the acid and you add extra hydroxide, it turns the phenolphthalein pink. Okay, and so I'll show you an example of that and what it looks like. But regardless, that's the chemistry, which is why we do the labs at the end to kind of give us our practical experience. So we still have to come back here and do our math. So we've got 1.3009 grams of KHP. The molar mass of KHP is 204.22 grams. Now remember, we're looking for moles of sodium hydroxide. Well, the good news is it's all a 1-to-1. So once we figure out we've got 1 mole sodium hydroxide, 1 mole of KHP. Either way, regardless of which substance we're talking about, it's going to end up being 6.3701 times 10 to the negative third moles. Now remember, I'm not quite done, because what was I solving for? Well, I'm solving for the molarity. So I'm going to go one more slide here, and molarity, remember, is moles per liter. So I take those moles, 6.3701 times 10 to the negative third moles, and divide it by the volume that we added, 4.120 times 10 to the negative second liters, and what I end up with is 0.1546 molar sodium hydroxide. Okay, I know it's a lot. I know that they're multi-step. You have the tools to do them. You just got to be able to know which steps to do when. Okay, there is one more example in your notes that's kind of a high-end type of problem. So I do want you to flip through and read through that example on page 163 and 164. And if I need to do a video, I can, or you need me to explain it. But, you know, at this point, we should be able to kind of go through the book and look at that example as well.